Here, the next topic is analysis of continuous linear state equation. So, the LTI system expressed in the standard state equation form and output equation form. LTI is nothing but linear time invariant system, okay, which is x dot equal to x plus pu. It's called state equation. Basically, this is a first order differential equation, and y equal to cx plus du, which is output equation. Now, in this analysis, what we will do, we will find the state variable response by solving for x of t and substitute x of t in y to find the output response. Okay, so we can do it in two ways. One is in time domain, another one is in s domain. So time domain, u of t is an input, y of t is an output, h of t is a system. So y of t equal to h of t. In time domain, we call this as convolution. Okay, so h of t times u of t, h of t convolution u of t. So the convolution involves integration. So basically, whenever you are solving problem, it involves integration or differentiation. Now, what we can do, we can convert that into Laplace domain or S domain. So u of s, h of s, y of s. So your y of s equal to h of s times y of s. Output equal to, h of s times u of s. Okay, y of s equal to h of s times u of s. Here we are finding the state response when there is a initial conditions involved. Initial conditions are nothing but, say if you are looking at a circuit, electrical circuit, say capacitor is initially charged or inductor is initially energized, something like that. So we are finding the state response when the input and initial conditions are given. So there is an input as well as initial conditions. So what we're going to do here, we're going to use the superposition principle. So first we will take only input, assuming initial conditions are 0, and solve for the state variables. And then again we solve it second time, assuming initial conditions are 0, input is given, or the second case, input equal to 0, initial conditions are given. So we'll find those two, combine those together to find out the final response. Now, so x dot equal to ax plus pu. Here I'm assuming 0 input. So if it is 0 input, u equal to 0, x dot equal to ax. Now, for example, consider x dot equal to scalar a, small ax. Okay, when I convert this into time domain, xt equal to e to the power of at times x0. x0 is the initial condition. E to the power of at, when we expand that, it's going to be 1 plus at, 1 plus 2 factorial a square t square plus 1 over 3 factorial a cube 3t cube plus etc etc. Now I'm going to apply the same principle here, x dot equal to ax. Here my a, capital A, is not a scalar quantity. Okay, it has it is in matrix format. If it is 2 elements, then 2 by 2 matrix, or 3 elements in the sense state variables. If there are 3 state variables, it's a 3 by 3 matrix. Okay, so x of t equal to e to the power of at x0. So e to the power of at equal to I plus at half 1 over 2 factorial a square t square plus 1 over 3 factorial a cube 3t cube plus etc etc. X of t equal to e to the power of at x naught. Now this e to the power of at, I'm going to represent that as phi of t, where phi of t is called state transition matrix. Okay, so here is the first example how to find this state transition matrix. So here is the example, we're finding the state transition matrix. So the given system, x dot equal to minus 2 0 1 minus 1 x1 x2 plus 1 0 u. Okay, that's the state equation. From there I can tell this is the A matrix, minus 2 0 1 minus 1, and I found A square by doing minus 2 0 1 minus 1 minus 2 0 1 minus 1. Multiplying these two, I end up with a square. Same thing, I found a cube, which is a square times a, and multiplied a square with a, end up with a cube. So and so on. I can find a to the power of 4, a to the power of 5, something like that. But I'll stop it here at a cube. So phi of t equal to e to the power of at, which is equal to I plus at plus 1 over 2 factorial a square t square plus 1 over 3 factorial a cube t cube plus etc etc. Now phi of t equal to, I substituted values I and a square and a cube and so on. Okay, now I'm going to separate the individual terms. So when I separate individual terms, I have 1 is right there, minus 2t is right there, 4 over 2 factorial t square minus 8 over 3 factorial t cube plus etc etc. That's the first term. Second term is everywhere you see 0, so second term is 0. Third term 0 plus 1 t minus 3 over 2 factorial t square plus 7 over 3 factorial t cube etc etc. And the fourth term is 1 minus t plus t square over 2 factorial minus t cube over 3 factorial etc. So when we simplify this, this is nothing but e to the power of minus 2t, that's 0. Here if we separate everything, it is, we will end up with e to the power of minus t and e to the power of minus 2t, and this is nothing but e to the power of minus t. Now the 0 input response is phi of t x0. So I already found phi of t multiplied with the initial conditions 2 and 3, so that's x1t x2t. This is the state response with the 0 input. Okay, 0 input state response. Now whatever we did here, this is a little bit hard way because I solved it in time domain. So in the next video, what I'm going to do, I'm going to solve this in frequency in S domain. Thank you.